but I'm going to effort. Okay, so what I want to share with you today, and I hope you find interesting, fun even, is a new first order theory for relativistic fluids. This is a work that I've been carried out principally with Olivier Sarbach and Felix Salazar, Carlos Gabarrete, Alma Mendez, and Guillermo Chacon are part of the group that we are working in this project, and the results that I'm going to show to you today were principally obtained. Well, the macroscopic part we worked with Felix, and the microscopic with Carlos, who is a professor in Honduras. So this is more or less the contents of the talk. First, I'm going to give some motivation, and then I'm going to go straight to the proposal of the new theory and the results. Then I'm going to go through the kinetic background, the kinetic foundation for the proposal. I'm going to address some preliminaries on the binary mixture, which we're kind of trying to work on. It's pretty complicated. And what I want to show you is the structure of the cross effects in plasmas, which we don't have yet, and we will not have for many years, I think, because it's a very complicated problem. But I'm going to show you the results of very old work, 2007, I think, which is a non-relativistic case. Let's show you the structure of the constitutive equations when you have mixtures of ions and electrons subject to an electromagnetic field. That is the heat flux and the electrical current, how they couple to the gradients in the system. So the main motivation is, I'm going to try to not to be too precise in the mathematics. Some equations are merely symbolical. I just want to show you the structure of the theory. So I apologize in advance if there are a lot of symbols. You can ask me if there's any question. So the main motivation is that relativistic hydrodynamics is still an open problem, particularly the dissipative case. As far as I know, in many applications, only viscous effects are taken into account. However, thermal dissipation, even if it's not very important, cannot be completely neglected. It's not consistent to throw away to keep the viscous dissipation and to not take into account the thermal dissipation. It cannot be zero. They cannot be simultaneously zero. So what's the main problem? We have the transport equations for a relativistic gas. We have made two equations. The first one is the conservation of the mass, J. Here is the particle current, and the balance equations for the stress energy tensor. I'm considering here an electromagnetic field, which can be external or consistent with Maxwell's equations for the system. And what we're used to seeing is just the particle current in the direction of the hydrodynamic velocity. Here using hydrodynamic velocity, N is the particle density, E is the internal energy, P the hydrostatic pressure, and the terms that are marked in red are the dissipative contributions to the energy and momentum sensor. This is the pressure deviator, which has to do with the bulk viscosity. Q is the heat flux, and tau it's related. It's related to the shear stresses, the shear viscosity. So if we introduce these equations in this, this definition, this decomposition, this 3+1 decomposition in the balance equations, we obtain a set of hydrodynamic equations for the dissipative. The first one is the continuity equation, which we are very used to, and it's in the relativistic case it has exactly the same structure as in the non-relativistic case. However, The second one is the internal energy balance. And well, the Euler side is this one. All the dissipative effects are on this side. And this we have in the non-relativistic scenario, this term also, but this term is exclusive for the relativistic fluid. And it's a quite complicated term. It of course depends on what is the constitutive equation for the heat flux. This is the momentum balance equations. Again, the equilibrium side is on the left-hand side, and on the right-hand side, we have all the dissipative effects. The first term survives in the non-relativistic limit, and well, without this one over here, and these are all, well, I think this one also. This comes from the it's also featured in the non-relativistic case. And the dangerous one is actually, I think, this one and this. So the system of equations, of course, is not closed. We need closure equations or constitutive equations for the heat flux and for pi and for T. Those we can obtain in a phenomenological fashion or from kinetic theory. What one has is that in the relativistic case, the constitutive equations for the viscous effects have exactly the same structure as in the non-relativistic case. However, the heat flux is a little bit more complicated. In the non-relativistic scenario, we only have Fourier's law, which says that heat flux is proportional to the gradient of the temperature. However, we have here an extra term which couples the heat flux with the hydrodynamic acceleration. That is if we work in a purely phenomenological way by imposing the non-equilibrium extension of the second law of thermodynamics, that is having a non-negative entropy production. However, kinetic theory seems to, in principle, predict couplings between the dissipative fluxes and the gradients of the state variables. In this case, it would be the gradients of the temperature and the gradients of the density. These relations, as I mentioned, they reduce to the usual Fourier constitutive equation. This one vanishes and this one also vanishes. And the Navier-Newton relations are the ones over here. So what's the problem? We already know that the Fourier, the heat equation in the non-relativistic case allows for propagation with arbitrary velocities. So that's a problem in the relativistic scenario. But it's even worse because the problem, if I couple the previous equations with these constitutive equations, which is the one that is obtained from the phenomenology, or even with this one, the system is unstable, which is a non-physical result because I'm not putting anything here that may make the system blow up. I should just get acoustic propagation in the case of the neutral gas. So we have a problem with causality, and we have a problem with instability. And actually, I think I have the reference in the next slide. We showed that the problem is ill-posed. So it has all the bad features that you can think about if you use either of these constitutive equations.
So I have a question. So the instability that you have, it's because from the beginning, the Q you are proposing is from kinetic theory. You introducing this, let's say, infinite velocity, or it's because you are modifying the equations and now are not hyperbolic anymore?
They're not hyperbolic, actually, they're parabolic. And this one leads to a parabolic stable, just in the moving frame. If you move from a moving frame, if you have a hydrodynamic velocity that does not form surfaces and you cannot stand in a moving frame, then this one is unstable. And this one over here is always unstable. Actually, you end up with a second derivative term, which always leads to an unstable mode. If you write a dispersion relation instead of being cubic, which is what you get with Navier-Stokes in the non-relativistic case, it turns to be of fourth order, a fourth order polynomial, and always has a positive root. So any perturbation will grow exponentially. And this is what has been called generic instabilities, and it was shown. I have the reference at the end of the slides by Hiscock and Windham, and they call them generic instabilities. And they classify this type of instabilities as generic, and they concluded that all first order theories were going to have these instabilities. So that led to the consideration of second order or extended theories. The ones like Israel and Stewart, which basically, this is the non-relativistic case. I didn't want to put all the equation, but basically, the problem with instability comes from the heat flux. The viscous terms do nothing to the system. It's perfectly fine. The problem is always with the heat flux. So instead of having instead of having the constitutive equation as a constraint to the system, you introduce you end up considering the heat flux as an additional dynamical variable, and you introduce an evolution equation for heat flux by introducing, not by hand, but kind of a relaxation term with some characteristic time, which is unspecified. So since you can play with this parameter, then you can stabilize the system. However, it's not that simple, because in some sense, this parameter has to be small, because this is the part that needs to dominate. However, it can be shown that well-posedness and stability in an arbitrary frame kind of require that tau is big enough. So in one sense, you need it small, but for the problem to be well-posed and stable, then it has to be large. So it doesn't solve the problem completely, but it worked for many decades. So why are we happy? We're very happy because first order theories made a comeback, a very successful one up to now, or very promising, in the shape of general theories. So these theories have been recently proposed, and it's like kind of a change of mind. Behind this, what the new theories say is they're going to think about a completely general particle current and a completely general energy momentum tensor. And the closure equation that I'm going to propose couple all the quantities in J and T with all the derivatives to the corresponding rank. So in principle, they say, I know nothing about physics, I know nothing about Fourier or experiments or anything. I just think that all of this is possible. And let's see which restrictions do I need in the parameters for the problem to be well-posed, to be causal, and to be stable. Let's just see what happens. And well, all of this is to, of course, to first order. This indicates just second order in derivatives.
So this expansion is Taylor expansion in some kind of equilibrium state, or how is this?
Well, this the end. Yeah, I didn't mention that. Sorry. What happens is that in in the relativistic scenario, we know what the state variables, that is the particle number density, the internal energy, well, the temperature, the internal energy, and the aerodynamic velocity is. However, out of equilibrium, we can choose whatever we want. We have a family of different representations and frames, and the condition is that they all coincide in equilibrium and they coincide with the state variables. So in that sense, I can think that, well, here n is going to be just the particle number density in equilibrium, in local equilibrium, and then the deviations I can expand in other derivatives.
Okay, you are expanding in terms of quantities you already know very well in principle, right?
That you already know.
Because n, I mean, your three parameters, nu, epsilon.
The coefficients.
Only the coefficients, right?
Yeah. Well, you have an equilibrium situation, and then the derivatives, the gradients and the derivatives, they take the system away from equilibrium. So we are thinking here that everything can couple to everything. If you see the heat flux, Fourier tells you that you just have this term over here, that just like the gradients of the temperature can drive a heat flux. However, here we propose, well, it's proposed that all gradients in the system, this is U dot. I mean, all vector derivatives can drive a heat flux and produce dissipation. And while here we're considering also the electromagnetic field. So the new theories propose to write all the out of equilibrium quantities in terms of every derivative to first order to the corresponding rank. I mean, scalars with scalars and vectors with vectors. And we're going to look to restrictions on the coefficients such that we are led to a well-posed Cauchy problem. It is causal, it has to be stable, and it has to be consistent with the second law of thermodynamics. So imposing that, one can get some very complicated restrictions on the parameters in order for these four conditions to be satisfied. However, it's not that terrible since we can reduce the number of coefficients to just combinations of those coefficients which are invariant if you change what is called the frame, which I'm going to explain in a couple of minutes, and the representation. So why can't we have all these coefficients? Basically, well, as I said, we have the freedom to choose the out of equilibrium quantities, variables, as long as they go to the correct limit in the equilibrium case. And also, we impose, I mean, we can reduce the number of unknowns by imposing that invariance of these combinations of coefficients if you change either the frame or the representation. And these three parameters correspond to the thermal conductivity, the bulk viscosity, and the shear viscosity. So you can reduce all these coefficients and the restrictions, the conditions you have on them to just 3. However, that's very general, and the restrictions are they are inequalities, and they are very complicated, and they are hard to verify. So what we propose is a particular frame. As I said, the frame is the way in which you choose the out of equilibrium quantities. You have to find, I mean, you have to use two conditions, two scalar conditions and one vector condition which is going to define from the out of equilibrium value for the general variables that include the non-equilibrium part and the equilibrium part, how you land into the equilibrium variables N, T, and U. So what we propose is a frame which we call the trace fixed particle frame, and it consists in fixing the current to its equilibrium part. Your N is the equilibrium variable, and U also. So in that sense, we're in a particle frame. So this first equation here, J, these are the equations in the previous slides. This is the general current, and this is the general stress momentum tensor, the stress energy tensor, sorry. And we are choosing, we are imposing that J still out of equilibrium is just N times U. So that's how we fix one of the scalar quantities and the vector quantity. And in order to define or to fix the temperature, we're going to take the trace of the energy momentum tensor. That's the trace fixed part. So the particle part frame corresponds to this equation, and the trace fixed to this equation over here. And these equations are mostly the same. We're just fixing the time part of the current to minus N, the orthogonal part to 0, and the trace is going to always be the one given by the equilibrium case. And I just wanted to contrast it with what you probably know, which is Eckart's frame, in which this is also a particle frame. However, the temperature is fixed through the internal energy, which one would think in principle may be, or well, it was kind of the natural generalization of the non-relativistic case, in which you fix the temperatures through the internal energy. However, this proposal over here, as I'm going to show you, comes from kinetic theory, and it also is able to fix the temperature. I can invert this relation in order to find the temperature. And it also reduces to the internal energy in the non-relativistic limit. So in the non-relativistic case, it's the same as the Eckart frame. Okay. So this is a summary of the results. We have the balance equations with this expression for the current and for the energy momentum tensor, in which I have fixed this coefficient and this combination, the two coefficients, to the ones in equilibrium. However, in T mu nu, I'm going to have a non-equilibrium contribution, which I call epsilon over here, and this is going to be the pressure deviation. So in Eckart's frame, we don't have these parts. Well, I mean, this one we don't have this epsilon. And we found from kinetic theory and by making transformations from the Eckart frame, we found these constitutive equations. This one is the same as usual. This also remains untouched. And this epsilon is non-zero, and is actually related to the divergence of the hydrodynamic velocity. So this is the constitutive equations in the trace fixed particle frame. And these ones, I mean, you substitute these constitutive equations in this in the current and in the energy momentum tensor, introduce them in the balance equations, and you get a system of equation. However, there's still another freedom which corresponds to what we like to call a change of representation within the same frame. Since we are working in a linear theory, just the first order in derivatives, I can always add to these constitutive equations a multiple of these combinations. Why is that? Those equations, if I equal these to zero, they are Euler's equations for equilibrium. So in the expansion, these quantities are really not zero, but they are second order in derivatives. Actually, you can see that from the first, one of the first here, over here. The continuity equation is always equal to zero, but these quantities over here are second order in derivatives. So this combination, these two terms are second order in derivatives. And the same with these ones over here. So I can add a multiple of this or a multiple of this to the constitutive equation and still retain the first order in derivatives. So that freedom corresponds to a change in representation in which, for example, if here you choose gamma 1 equal to 1, then you can get rid of T dot, and then the constitutive equation is going to be just in terms of the divergence of the hydrodynamic velocity. Or you can choose it as to eliminate this one, and then you will have one, two. And the same with the heat flux. So you can have the heat flux in terms of the gradient of the temperature, the acceleration, and the electric field or the electromagnetic field, or gradients of the particles. So in that way, you can change the forces that drive the sympathy process.
I'm sorry, what
Yep.
is D?
Sorry?
What is D?
Small d or
Yeah, small.
that's the dimension. Sorry, I didn't comment that. These results are in the d plus 1 dimensions. And actually the result that we checked were for d equal 2 and d equal 3 for hard spheres and hard disks models.
Sorry, theta here is the temperature, the electron temperature, or what is theta here? In the yes, here.
This one, no, it's the divergence of the divergence of the velocity.
Okay, because I was
It's
thinking that
expansion, yeah.
you say that this is constitutive equation, but
Yes,
I was-
actually, this is the gradient of the velocity.
okay.
So this is a trace the symmetric, this is an antisymmetric, and this is
Yeah, because the
Okay,
letters, I was wondering if this can be interpreted like an equation of state, but not, right?
No. No.
Okay.
No, because also this epsilon over here, it's a dissipative
Mhm.
component. This part over here. It's a non-equilibrium contribution. So the results is that when one linearizes the system around a global equilibrium state in flat spacetime, the system is strongly hyperbolic. It's causal. If this inequality is satisfied, which we verified for the hard spheres and hard disks case, in d equals 3 and equals 2. And also, instead of having the generic instability, which was obtained with Eckart's theory, we get just acoustic modes propagations, which are damped by the Stokes coefficients. So it's just a direct generalization of the non-relativistic case. So there's no instability, the system is strongly hyperbolic, and it's causal. Also, the second law can be verified to the first order gradients. The full nonlinear system leads to a well-posed Cauchy problem. And as I said, we verified that the conditions for all of this to happen is satisfied for hard spheres and hard disks. So it's a first order theory for dissipative fluids, which leads to a consistent system. Consistent in the sense that it satisfies the requisites of causality and being well posed, and also it leads to what one expects in the case of the free fluid, which is just propagation of acoustic modes. So, yeah, okay. So with the rest, well, yeah, for the following 2 or 3 slides, sorry, I'm going to try to explain you how did we get to the trace fixed particle frame. It can be thought of as just, well, you can fix the UU component of team UNU, which is what Eckhart does, and it leads to the instability and all that. Or, I mean, you need one vector to scalar. So what's kind of ambiguous is how to fix the temperature. That's kind of the tricky one. So you can think macroscopically, just that you decide to fix the trace of the energy momentum tensor instead of fixing the UU component, the 0,0 component. However, this trace fixed particle frame can be actually what motivated us to choose this frame was the kinetic theory of gases, of relativistic gases. So the kinetic theory of gases describes the fluid, the macroscopic properties of the fluid in terms of the evolution or the characterization of the system through a distribution function, which I call F. And yeah, I think I changed the notation. I didn't see that. This is J, the current, sorry, it's J. It's just kind of the average of 4 momentum, and the stress energy momentum tensor is well, it's this integral over here. So you can get all the macroscopic quantities through averages over the distribution function. And the Boltzmann equation gives me the evolution of the distribution function. So this looks like a very simple equation, but it's actually pretty complicated. What we have on the left side is this operator, which is not complete here, I'm sorry. This is, I need the curvature term and the electromagnetic force term. And the right-hand side is the collision side, and it accounts for binary collisions between molecules. So it's just a change in occupation number because of collisions in the system. And
sorry, this distribution function, which thing is represented? It's a distribution of particles, species of particles, or what is being physical?
It's the occupation number in phase space.
Mm-hmm. Okay, you are solving in phase.
Exactly, it's in phase space, and it's just how many particles do you have with certain moment at certain time with certain position and certain moments. Yeah. So what it's interesting here, interesting and complicated, is that we can write the Boltzmann equation in terms of non-dimensional quantities, which are the ones with the bars. And here you kind of have to introduce some scaling parameters. And it turns out that these two terms scale differently than this one. So here you can kind of separate regimes. If you don't have if you have a neutral gas, you don't have this term over here. Okay, and you just have that this is the collision term, and it's I mean, if you have this parameter being small, then collisions dominate. When you have the electromagnetic term, then you have two competing parameters. Here, this parameter over here is called Knudsen parameter, and it's the ratio between, this is the mean free path of the particles, the distance they cover between collisions, and LS is a macroscopic length, a characteristic macroscopic length, which kind of measures the length in which the gradients occur, the length that a particle has to cover in order to see a gradient of the temperature, for example. And we usually choose it of the order of the size of the system itself. You need at least be able to see one gradient, one unit of gradient within the system. If not, it doesn't make any sense. And this other one is the characteristic electromagnetic scale, compared also with the size of the system. And this is going to be thought of as Larmor radius, for example, if you have a magnetic field. So these two parameters, in terms of the ratio of the length between collisions and the radius of an orbit around a magnetic field. So we can separate three different cases. The case where we are treating here is the one we call the weak field. And in this case, collisions dominate. So particles collide a lot before completing an orbit. And the electromagnetic force acts like just an external force. Okay? There's another regime which is, it's kind of intermediate, really, but it would be the strong field case. In the strong field case, it's quite difficult because we think that these two scalings are roughly similar. So you have to take into account both terms. You don't have the electromagnetic part dominating or the collision part dominating. So that's the top one because the equation it's very hard to solve. And then the other extreme case is the Blasov case, in which collisions are completely, you can neglect collisions and just think about Blasov's equation. So in this case, in which collisions dominate, we use the Chapman and Scott method to solve the Boltzmann equation, in which we expand the distribution functions in powers of that small parameter. To lowest order, we get the local equilibrium distribution function, which is a Maxwell-Jungner distribution function, which is the relativistic, kind of a relativistic Maxwell-Boltzmann distribution function. And the first order, well, okay, one linearizes the collision operator, and it's led to two equations to order 0. We just have the collision kernel equal to 0 and the Jungner distribution function to solution. And to first order, we get this equation, which is An integral equation, this side I already know. Because I know the local equilibrium distribution function, and my unknown is F1, which is one that is going to have all the information about dissipation. And this is the point that I wanted to write with all these kinetic theory equations, is that when you're going to solve this equation, this one over here, in order to get F1, which is the one that's going to give you all the constitutive equations of the dissipation terms, you end up with two terms, okay? You need to invert this integral operator. However, for existence of the solution, we need to project the right-hand side into the complement of the kernel of the operator. I cannot have before, in order to invert, I cannot have on this side things that lie on the kernel of the operator. So what I do is I just project here in the orthogonal complement of the kernel, invert the operator, and then add an homogeneous solution. You can think about this as kind of the solution to the homogeneous equation and to the particular also. It's something like that. So what the trace fixed particle frames has in particular is that the conditions that specify the frame are consistent with the quantities that belong to the kernel of the collision operator. The consequence of that is that when it can be shown that the homogeneous part is the one that can that allows for a change of frame. Okay, I mean this part over here is the one that you need to demand for existence of the solution. However, you get a family of solutions from the homogeneous part, which is a linear combination of the elements of the kernel. And the way to obtain a unique solution is by imposing what is called subsidiary conditions. These conditions are exactly the ones that tells you how you state variables. So these conditions over here, over the first order distribution functions, are exactly these ones. Okay, so in the macroscopic sense, I impose these conditions, but they have really a microscopic foundation. So this part in red corresponds to the trace fixed particle frame, and they lead to these equations for the current for the self-energy tensor. And just to compare, these are Eckhart closure equations, which is the 0,0 component of the energy momentum tensor. And this one is the same in both frames because they are both particle frames. So these are the quantities in the trace fixed particle frame, and these are the quantities in Eckhart. Okay, so that's the kinetic theory underlying the trace fixed particle frame. So we have these general first order theories, and what we're doing is actually we obtained a theory which is hyperbolic and causal and stable from kinetic theory, and it has the form of the general first order theories. So, and this are the kinetic foundations, and the mathematics behind all of this is really elegant and beautiful, and I don't have time over here today to show you all the details. So what we're trying to work on right now, and it's getting pretty messy. Well, no, it's nice. It's a little bit more tedious, but it's going fine. It's considering two species. In the case of two species, we have two Boltzmann equations, and these are collisions between the same species, and these are cross collisions. This problem is even more complicated because you can imagine that if I write these equations in terms of non-dimensional quantities, then I'm going to have more parameters for the for collisions and for the electromagnetic interactions. The problem is that in order to try to find try to apply the Chapman-Enskog method to these equations, I have to fix the regime. I cannot do it in general. Okay, so maybe you can say, well, these are electrons, these are ions, and I'm going to neglect electron, and just keep electron ion, for example. Okay, so you can play around with different conditions, but in principle, we have two Boltzmann equations, one for each species. We have balance equations per species, and we have a balance equation for the total stress energy tensor. And once again, in order to linearize the problem and try to find a solution, one has to decide which regime to work on, and that may depend on the kind of system that we are treating, the densities, the temperature, the characteristic, the mean free path, the intensity of the electromagnetic field.
5 minutes.
Okay. So, what one should get for the binary mixture are these, this is the current, this is the stress energy tensor, and the constitutive equations look like this. And these are what I wanted to show you. Maybe don't pay attention to this one. I think the interesting one is this one. This is the vector constitutive equation. And what you have is this is the heat flux. This is the particle current, the non-equilibrium parts of the particle current. And actually, what you have what are called cross effects. So this L11 corresponds to the heat flux coupled to this force over here, which is the direct one, the one that we had when we had a single species system. But now you have a coupling with this second quantity, which is kind of diffusion, and it has the electromagnetic force also. And also the non-equilibrium current is coupled with the heat force, the thermal force, and this is going to be the direct coupling. Kinetic theory says that this matrix has to be symmetric, and it's called on the side of reciprocity relations. But what I wanted to emphasize is that in the binary mixture, we get cross effects, not direct effects. And the cross effects in plasmas, they are very interesting, more complete. However, these results, which I wrote down here just kind of symbolically, are for the non-relativistic case. And actually, one writes a diffusive force, which depends on the range of the concentration of the pressure and the electromagnetic force. Then the heat flux is coupled with the gradient of the temperatures is not non-relativistic. So to the gradient of the temperature and to the diffusive force. And the electrical current is coupled with the gradient of the diffusion force, which is a direct coupling, and with the gradient of the temperature, which is the cross effect. What I wanted to also highlight is that all these coefficients are different. So if you're going to think about this first line as just thermal conduction, then you're going to have different thermal conductivities in the direction which is parallel to the gradient of the temperature, which is kind of clear. And then you're going to have another transport coefficient in the direction which is orthogonal to the gradient of the temperature and the magnetic field, and another one, different one, in the direction of the magnetic field. And the same for the currents. So you're going to have different electrical currents depending on the direction of the gradient of the temperature and of the magnetic field. So this is kind of a summary and final remarks. We found first order theory, which is well posed, hyperbolic, everything you would like it to be. It has the form of the general B, D, and K theories, first order theories, but it is obtained from kinetic theory, and it can be it's obtained from kinetic theory. You can generalize it to different systems, for example, the binary mixture and an ionized fluid, and work in progress and future work treat the binary mixture of neutral fluids. Well, to check which are the relevant regimes. I mean, when you ponder electromagnetic effects and collisions, and try to get these kind of equations, but for the relatives. And that's it.